Okay, so in this video, we're now going to look at the source-free RL resistor inductor circuit. So again, we're trying to understand what happens to a circuit, what response will an inductor produce when it remains as a sole supplier of energy to a resistor in a circuit. So we start by looking at a basic circuit containing an inductor and a resistor. So if we consider a circuit like this one here, what happens here? So since current is flowing in this direction, we expect that for the inductor this side, since current is going in that clockwise direction, we expect that to be positive here and minus in that sense. So when evaluating for such a problem, let's take it that when time is equals to 0, so just when we start observing our time, so for time is equals to 0, it so happens that the current in the line is equal to some initial current in flow. Let's take it as I0. Now, what happens here? Firstly, if we tried to use Kirchhoff's voltage law to loop around this circuit, we'll notice that we're going to have the sum of the voltages around that closed circuit to be the voltage across the inductor plus the voltage drop across the resistor being equals to 0. This is in accordance to Kirchhoff's voltage law. From here, we can now try to bring in what these voltage expressions are going to be. From Ohm's law, the voltage drop across a resistor, we know to say it's going to be given by the resistance value times the current passing through. The current passing through, we're taking it as I. The resistance value for that resistor is just R. Well, for the voltage drop across an inductor, if you recall when we introduced inductors, the voltage drop across an inductor is going to be equal to the inductance multiplying the change of the current through it with respect to time. Based on this, we can substitute those expressions so that we have the I dt plus I R equals to 0. And then in this case, we want to solve this expression so that we have I. We solve this for an expression for I. Now to do that, of course, we're going to use separation of variables again. It's a method of solving differential equations. We used it when we looked at the resistor capacitor circuits. So first, we'll try to isolate I. You can first start by moving IR to the right side so that you have L di dt equals to negative IR. So L can go to the right. You can cross multiply the dt also to go to the right. So now you have di is equals to I L R dt. So these two are still R there and I there. The L, the L will go down, not like that. Yeah, looked too much. So you have I and R with the minus and the dt multiplying, but the L will divide down since it is in the numerator on the left side. Now you want I to join the di on the left side, so you divide both sides by I, so that now we have 1 over I di on the left, and the negative R over L dt on the left. These are constants. One is the inductance, the other is the resistance of that resistor. At this point, you can now integrate both sides. On the left side, when you integrate, you're going to have ln I. On the right side, when you integrate from time is equals to 0 to some unknown value of time t, you'll notice that since R and L are constants, you just introduce t as a parameter. The integral of dt will be t. Here we can say we can also bring in some constant if you do not have the limit. But if we say we are integrating from time is equals to 0 to some value of time t, meaning we have the limits of integration, we can argue to say that this is going to be from 0 to t. In such a case, what happens to our expression? So of course, on the left side, we can also say that this was changing from what the current was, since this was an integral in terms of current. We can say this was changing from the initial current we had, which is I0, to some final value of current I at some time t. So with this in mind, what happens? We want to find what I is. So of course, when we substitute the limits first, we can say this is going to be, we know it's the upper limit first, I at some time t minus ln the initial current we had at times equals to 0. On the right side, we're going to have minus R over L and then t, since when we put 0 for the second part, it's just going to be 0. So this will remain just like this. Now what we're trying to do is we want to make I the subject of the formula. So to do that, we can utilize a number of techniques, but basically still just logs. Since here you're subtracting two log expressions, we know to say if you have ln A minus ln B, this is the same as just ln A over B. So utilizing that property, ln I minus ln I0 will just be ln IT over I0 being equals to negative R over LT. At this point, you can get the antiln on the left and on the right. On the left, the antiln will eliminate the ln, so that now you have only I function of t over I0. On the right, you have e to the power negative R over L. So this is what I'm calling the antiln. Since what we want is what IT is going to be, cross multiply, so that now you have I0, the initial current, and then e to the minus R over L, I wrote t, over L times t. So this becomes the response from an inductor when it is the only source in a circuit that contains an inductor and a resistor. Now this, just like for a capacitor, we see that this is the natural response of an inductor in a circuit when there's no any other source present. For this type of circuit, we can also define a time constant. For a capacitor, we saw to say that the time constant tau was just equals to RC. That was for a capacitor. For an inductor, the time constant here will be defined as L, the inductance, over R. This is for an inductor. So if we did that, if we tried to see the time constant there, you will notice that this R over L, it can be seen as, let me write the whole power there. This RT over L, it can be seen as T over L over R. So that this now can be taken as tau. So that now the response from our inductor can be viewed as I0 E minus T over the time constant. So now it takes shape. It comes to look like the response from a capacitor. The only difference is when we had a capacitor, its natural response was in terms of voltage. And this was V0 e to the minus t over the time constant. So this was the natural response from a capacitor in a source-free RC circuit. For a capacitor, the time constant, we saw that it was equal to RC. For an inductor, which is here, we saw that in this case, the time constant is the inductance over R. So just in case you want to compare the two, it makes it easy for you to remember them. Of course, having found the expression for the response from an inductor as this, it makes it easy for you to find everything else. Because if you have the current, you can easily get the voltage. Again, this one here was just showing it for the response from a capacitor. But we continue with our discussion of an inductor. If let's say you are able to get the response from that inductor, but now you want what the corresponding voltage would be, you can still just go back to Ohm's law. Since this is the response that the inductor will be given, meaning this is going to be the current that it will be supplying. So if this is the current it is supplying in that circuit, we can determine what the voltage across the resistor due to the current coming from the inductor, what will it be at that same time t. By Ohm's law, voltage is current passing through the resistor times the resistance itself. Since we are saying the inductor will be feeding the circuit with that current, it now implies that for that resistor, as that current comes through, that current is I0, e to the minus t over tau. As that current comes through to pass through the resistor, of course, that is going to end up being our voltage value, our voltage drop across the resistor. So that now we can see it as I0 R multiplying e to the minus t over tau. This becomes the voltage drop across the resistor. Of course, we can now easily get what the power is going to be and finally what the energy absorbed is going to be. But more importantly, let's move on to look at